Welcome to all of you. Now we discuss MCQ 2023 paper CC-12 semester 5 under CBCS Mathematics Honors University of Calcutta Group Theory 2 and Linear Algebra 2. Question paper 23 paper CC-12 Mathematics Honors. Question 1a. Let G be a cyclic group of order 36. Then what is the correct option? Let G be a cyclic group of order Mn, where GCD Mn and n equal to 1. Then G is isomorphic to P cross Q, where P and Q are two cyclic groups of n and n respectively, of order m and n respectively, and where of order m and n respectively, where order of P equal to m and order of Q equal to n. Now here G is a cyclic group order 36, so 36 equal to 4 into 9, and GCD of 4 and 9 is 1. So by this theorem, G is isomorphic to Z4 cross Z9, because order of Z4 is 4 and order of Z9 is 9. Hence the correct option is 3. Question 1b. Order of the element is order pair A, this permutation 1, 2, 3 in K4 cross S3 claims 4 group K4 and S3 a symmetric group S3. Now we have the theorem. Let H, K be two finite groups, then the order of the element AB in the group H cross K is the LCM of order of A and order of B. Now this element A belongs to K4 claims 4 group, and A not equal to E being the identity of this K4, and the permutation 1, 2, 3 belongs to S3 symmetric group S3, and order of A equal to 2 because A belongs to claims 4 group and every element other than the identity has order 2, and order of the permutation 1, 2, 3 3 cycle, length of 3 cycle, and this is equal to 3. And LCM of 2 and 3 is 6. So order of this element A and the permutation 1, 2, 3 equal to 6. And correct option is 4. Next question C. It is true that automorphism Z is isomorphic to what? Now we have the result. If G is an infinite cyclic group, then automorphism G is a group of order 2. Let phi maps Z plus to Z plus, Z with the set of all integers be an automorphism. Since 1 is a generator of the cyclic group Z plus, and phi 1 is also a generator of the image group Z plus. And since the only generator of the group Z plus are 1 and minus 1, phi of 1 equal to 1 or minus 1. If phi 1 equal to 1, then phi n equal to n for each n belongs to Z. In this case, phi is the identity automorphism. If phi 1 equal to minus 1, then phi n equal to minus n for each n belongs to Z. So there are only two automorphisms of Z plus. That is order of automorphism G is equal to 2. And since Z2, set of residue classes Z2, this contains class Z2 and class 1, and order of Z2 is equal to 2. Hence, automorphism Z is isomorphic to Z2. So correct option is 2, Z2. Next question 1D. If F maps G to G such that Fa equal to a to the power n is an automorphism, then what is the correct option? The subgroup ZG is the center of the group G, and ZG is the set of all those X belongs to G such that XG equal to GX for all G belongs to set group G. Let A, X belongs to G, group G. Then a to the power minus n x a to the power n whole to the power 2 this is equal to a to the power minus n x a to the power n into a to the power minus n x a to the power n. This is equal to a to the power minus n x a to the power minus n bracket a to the power minus n x a to the power n, and this is equal to e. So we get, after simplification, we get a to the power minus n x square a to the power minus a to the power n. Similarly, we have a to the power minus n x a to the power n whole to the power k. This is equal to a to the power minus n x to the power k a to the power n for any integer k. Now, f of a to the power minus n x a to the power n, this is equal to a to the power minus n x a to the power n whole to the power n. By the definition of f is fa equal to a to the power n. So obviously, f of these elements is this whole to the power n. Now, by this previous result, mathematical induction, we can prove this is a to the power minus n x to the power n a to the power n. That is a to the power a inverse whole to the power n x to the power n a to the power n. This a inverse, so f of a inverse into f of x into f of a. Now, by the definition of homomorphism, f x into f a equal to f of x a. And again applying this, f of a inverse x a. And so, a to the power minus n x a to the power n equal to a inverse x a, because f is injective mapping and it is isomorphism, so it is injective also, and composing from the right by a to the power n and from the left a to the power a inverse, and so we get this, and this a to the power n a to the power minus n, so this e, and a to the power n a to the power a inverse, so a to the power n minus 1, and this a to the power n a to a inverse, so a to the power n minus 1, and this a and a inverse is e. So we get a x to the power n minus 1 equal to a to the power n minus 1 x for all x comma a belongs to G, and then a to the power n minus 1 belongs to ZG for all a belongs to G, center of G. So correct option is 1. Next question E. If T be a linear operator on R3 whose adjoint operator T star is defined by T star x comma y comma z equal to 2x plus z comma 0 comma 0, then T x comma y comma z is what? Here R3 finite dimensional vector space, real vector space. So we compute this t by this way, and t star is this x comma y comma z, and this is equal to 2x plus z comma 0 comma 0. So we can write 2x plus 0y plus z, 0x 0 plus 0y plus 0z, comma 0x plus 0y plus 0z. So this matrix 3 by 3 matrix 2 0 1 for this 2 0 1 0 0 0 0 0 0, and this column matrix x y z, and we say x star x, and where is the star is the A bar whole transpose. A bar is the complex conjugate matrix. So T star for the standard basis alpha of R3. Now A star whole star is equal to A by the theorem of this transpose. This here A bar equal to A because A is the real matrix. All elements are real. So A equal to A star whole star. Actually, this is the transpose of this. So this. So T equal to 2x comma 0 comma x. But the better option is this way. You can compute this way. T. Let T star this mapping from R3 to R3 be with the adjoint of T, the inner product T. Then the inner product T alpha beta equal to alpha T star beta for all alpha comma beta belongs to R3. And then T is the adjoint operator of T. Let alpha equal to x comma y comma z, beta equal to a comma b comma c. In alpha, inner product of alpha comma T star beta is equal to alpha equal to x comma y comma z, T star beta equal to twice a plus c comma 0 comma 0. Standard inner product. So we get x into 2a plus c plus y into 0 plus z into 0. This is equal to a into bracket 2x plus 0 plus 0 plus b into 0 plus 0 plus 0 and plus c into x plus 0 plus 0. So we can write the inner product of this 2x comma 0 comma x comma a comma b comma c. So this is the T alpha by the definition of adjoint. This is the T alpha and this is the beta. So T alpha, actually alpha is the xyz, that is the T alpha is this. So T xyz equal to 2x comma 0 comma x for all x comma y comma z. So our triplet this belongs to R3. And this is the best way to compute this T star or T. Now note that so correct option is 2x comma 0 comma x. So correct option is 3. Correct option is 3. Note that let V and W are inner product spaces and T maps from V to W is a linear transformation. Then a linear transformation T star maps from W to V is called the adjoint of T if inner product of T alpha comma beta equal to inner product of alpha comma T star beta for all alpha belongs to V and beta for all beta belongs to W. And this T star, the adjoint of T, is also called Hermitian adjoint of T. Reference Hurston and Winter matrix theorem linear algebra page 354. If MT is the matrix of linear product T, a orthonormal basis of V, then MT star equal to MT whole star, that is equal to MT dash whole bar. This is the complex conjugate. That is the Hermitian adjoint of the matrix MT. MT is the matrix. Here T maps from V to V is a linear transformation and V is a finite dimensional vector space. And T star A star equal to T, A star whole star equal to T star into star, and AT plus S whole star equal to A bar complex conjugate of A into A star plus T star, where S comma T belongs to the L of V, linear operator of V, and set of all linear operator, linear transformations on an n-dimensional vector space V over the field F, and A belongs to the field F. And number 5, if V is a finite dimensional vector space over R or C, then V is an inner product space. Next question, option 2. Option 2. Sorry, option 3. Option 3. Next question, if the degree of the minimal polynomial of 200,040,006 is what? Let A is the matrix, given matrix 200,040,006. The characteristic polynomial of A is the determinant of A minus xi3, identity matrix of order 3. So this is equals to 2 minus x 0 0, 0 4 minus x 0 0 0, 6 minus x. So this is equal to 2 minus x, 4 minus x, 6 minus x. This is the psi x, say. This is the characteristic polynomial. As the minimal polynomial px divides the characteristic polynomial psi x and they have the same zeros, then px equals to x minus 2, x minus 4, x minus 6. And because there are three distinct eigenvalues, so minimal polynomial equal to the characteristic polynomial. So degree of the minimal polynomial is 3. So correct option is 2. Note that a monic polynomial is a non-zero univariate polynomial in which the leading coefficient is 1. That is, monic polynomial means x to the power n plus cn minus 1, x to the power n minus 1, plus dot dot dot, plus cx plus c0. And minimal polynomial of a square matrix A of order n over a field F is the monic polynomial P over F of least degree such that P A equal to the null matrix. And the characteristic polynomial phi x equals the minimal polynomial Px of the matrix A if and only the number of distinct eigenvalues of A is equals to the order of the matrix. So number of distinct eigenvalues of A is equal to the order of the matrix. Then characteristic polynomial equal to the minimal polynomial. And so here degree of minimal polynomial is 3, correct option is 2. Question G, let phi be the linear functional on R2 such that phi 2, 1 equal to 15 and phi 1, minus 2 equal to minus 10, then phi minus 2, 7 equal to what? If phi is a linear functional on V, then we know phi of CR1 alpha plus C2 beta this is equal to C1 phi alpha plus C2 phi beta. For all C1, C2 belongs to the field F, scalar field F, and for all alpha, beta belongs to V, where V be a vector space over the field F and phi maps from V to F. Here, V equal to R2. In this question, V equal to R2 and F is the real field R. And alpha equal to 2, 1, this 2, 1, and beta equal to 1 minus 2. So phi of C1 this alpha plus C2 beta is equal to C1 phi alpha plus C2 phi beta. So you can write this 2C1 plus C2 comma C1 minus 2C2 is equal to Phi of 2, 1 is 15 and phi of 1 minus 2 is minus 10. So we get, now we want to find phi of minus 2, 7. So 2c1 plus c2 is equal to minus 2 and c1 minus 2 c2 is equal to 7. So solving this, c1 equal to 3 by 5, c2 equal to minus 16 by 5, and then from 2, phi of minus 2, 7 equal to, put these values of c1 and c2, and after simplification we get 41. Alternate way, let alpha equal to x comma y belongs to R to be any element. Then phi alpha equal to phi of bracket x 1 comma 0 plus y 0 comma 1, the standard basis of R2. Phi xy equal to x into phi of 1 0 plus y into phi of 0 1, because phi is linear function on R2. This implies phi xy equal to c1x plus c2y. This c1 phi 1 0 is c1 and phi y0 1 is c2 for some c1 c2 belongs to real number. Now phi 2 1 equal to 15, so put here 2c1 plus c2, this 1 y equal to 1, this equal to 15, and phi 1 minus 2 is minus 10, and so c1 minus 2 c2 equal to minus 10, and solving we get c1 equal to 4, c2 equal to 7. So phi 27 equal to 41. So the correct answer is 41, that is option 3. Next question H. If VF is an inner product space and theta perpendicular, singleton set theta perpendicular is the orthogonal complement of the singleton set theta, where theta is the null vector in V, then which of the following is true? Let VF be an inner product space. Let W be any subset of the vector space V, need not be a subspace of V. The orthogonal complement of W, denoted by W perpendicular, is defined by W perpendicular equal to the set of all those alpha belongs to V such that inner product of alpha beta equal to 0 for all beta belongs to W. Note that this W perpendicular is a subspace of V. Let W equal to the singleton set theta. Theta is the null vector of V, because we are giving this theta is the null singleton set and W. And then for all alpha belongs to V, we have the inner product of alpha theta equal to 0, obviously. So W perpendicular, that is the theta perpendicular, singleton set theta perpendicular, this is equal to the set for all alpha belongs to V. So this is the set V, vector space V, whole vector space V. So correct option is this 3. Next question I. The signature of the quadratic form 5x square plus y square plus 10z square minus 4yz minus 10zx is, let Q is the quadratic form of this, so we can write the corresponding symmetric matrix is this 5 0 minus 5 0 1 minus 2 minus 5 minus 2 10. Let us apply the congruence operation on A to reduce it to the normal form. So A, apply R3 plus R1, adding R1, that is first row to third row, so we get this. Next, similar operation on column, so C3 plus C1, that is adding C1 to C3, so new C3 is this. Next operation R3 plus 2R2, third column plus 2 into R2, so we get this. Next operation C3 plus 2C2, this. Next operation R1 by root 5 and C1 by root 5, so this is the identity matrix I3. Then obviously here the non-zero rows 3, so rank of the matrix A, that is the quadratic quadratic polynomial, this quadratic form, this polynomial, quadratic polynomial, this A equal to 3, and index of Q is M3 because the number of positive ones in the normal form. Here number of positive ones 1, 3, so M equal to 3, and signature of Q is S, this is equal to twice M minus R, and the number of positive ones minus number of negative ones is equal to negative number of negative ones 0, so 3 minus 0 is 3, so signature is 3, correct option is 4. Next question, J. If X equal to this order pair A1, A2, Y equal to order pair B1, B2, the any two vectors are this V2, F, then the length of the vector 3, 4, this order pair, with respect to the inner product X, Y, this is equal to A1, B1 bar plus bracket A1 plus A2 into bracket B1 bar plus B2 bar is what? Let alpha equal to 3, 4. This belongs to V2F. Now, this inner product alpha alpha, this equal to this A1, A2, B1, B2. So A1, B1 bar. B1 bar is the complex conjugate. Here, B1 is the real number. So same B1 bar equal to B1, B1, and plus A1 plus A2 into B1 bar plus B2. So 3 into 3, 9, 3 plus 4, 7, 3 plus 4, 7, 7 into 7, 49, so 58. So norm, that is the length of the vector, is equal to square root of this inner product, this alpha, alpha, so root over of 58. So correct option is 3, root over 58. And this completes the MCQ 2023 paper CC-12. Thank you for watching this video.